Hello everyone, welcome to the second week of module on population ecology. In the last week's module, we looked at how can we mathematically think about population dynamics. We looked at how in the context of no limiting resources, populations can grow exponentially. We discussed this using discrete time population modeling followed by continuous time population modeling. Followed by that, we looked at how the resources are indeed constraining in real populations when the population sizes begin to increase, and this leads to intra-specific competition which limits the growth rate of individuals and populations, right. And that led us to the logistic population model. Okay. So, in this week we will look at more than one population. Specifically in this specific video I will talk about how two species compete with one another, what are the implications of two species competing with one another, and how can we mathematically think about competition. Now, species compete with one another in a variety of ways, predominantly for resources such as food, shelter, territories, and mating, as well as space. All of them have a common factor, which is that competition reduces the per capita growth rate of each other. Competition reduces per capita of interacting individuals. Of course, we already looked at one form of competition, which is intra-specific competition. Which is the competition within a single species. So, the way to think about this was we plotted the per capita growth rate on the y axis, and how does this vary with the population size. Under the simple assumption that the per capita growth rate declines linearly with population size and hits 0 when the population size hits a value of k, which sort of corresponds to carrying capacity. Under these assumptions, we obtain the logistic population model. dn by dt is equal to Rn times 1 minus n over k. Right. So, here R can be, we can call R as intrinsic growth rate. It basically means if there was no competition, what would be the growth per capita growth rate, and then K is the carrying capacity. So, this captured intra-specific competition. Of course, in reality many species interact with one another, and competition is a predominant mode of interaction. That leads us to inter-specific competition. Of course, inter-specific competition often acts on top of intra-specific competition. So, how can we mathematically express the inter-specific competition. So, we shall start with the basic assumption that there are two populations that we are two species that we are going to consider. Let us call them S1 and then we have another S2. Okay. Let us say that the population size of these are given by population sizes are given by N1 and N2 . N1 and N2, let us say their intrinsic growth rates are given by R1 and R2, and further let us denote the corresponding carrying capacities as K1 and K2. The exact species does not matter as long as the mode of interaction is competition between the two. Okay. Let us also further make a simplifying assumption that both of them are governed by the logistic population model in the absence of other species. So, therefore, dN1 by dt will be given by R1 N1 K1 minus N1 divided by K1. On the other hand, for species 2, dN2 by dt will be given by R2 N2 K2 minus N2 divided by K2. So, in the absence of other species, actually so far I have not included the competition between the two species. I am just setting the stage for the two, and now we can ask, how does competition influence and change these equations. Okay. So, what I will do now is that let us call this equation 1, let us call this equation 2, and this is given by the simplest form and the most widely studied form of these equations are given of the competition between two species are given by Lotka-Volterra equations. Okay. So, now let us get there slowly, thinking how competition affects both the species, how the interspecific competition affects both the species, how can we incorporate the effects of interspecific competition mathematically. To do that, let us again go back to the per capita growth rate curves that I drew, and let us do this for both the species one at a time. Let us do it for one species now, for species 1. So, species 1 has an intrinsic growth rate R1 and the carrying capacity K1. Okay. Now effectively when what this is telling is that the per capita growth rate reaches 0 when the number of individuals of species 1 is equal to K1. Okay. Now, what can happen in the presence if I add now a few more individuals who are of species 2. Let us remember that this x axis is N1. Okay. So, basically what we can expect is that the point at which the per capita growth rate hits 0 could happen earlier if there are now additional individuals to a system which has already reached carrying, which is already at a high population. So, we can sort of imagine sort of heuristically that this curve becomes more slanted like this. Okay. So, this is sort of one way to think about this. So, in terms of mathematical equations, how does this influence the equation for the growth of population 1? So, we can sort of write an additional term here. The term here basically is the effect of inter-specific competition. So, what this means is that if there are some individuals of species 2, it will reduce the per capita growth rate of species 1 even further. Okay. And we will make one further assumption that the effect of species 2 on species 1 is a linear function of species 2. So, basically what I am trying to say is that if I were to denote this as f1 of n2, basically it is the species 2 population that is affecting the species 1's growth rate. Okay. So, the basic assumption that we will make is as follows: this is a linear function of n2. More there are number of individuals of species 2, stronger the effect of the competition, more the quantitative effect of species 2, and we will denote the coefficient by alpha 1 2. Alpha 1 2 indicates the effect of species 2 on species 1. So, we have to read in the opposite way. Alpha 1 2 represents the effect of competition of species 2 on species 1. Okay. So, with this assumption we can now write down how the population 1 grows in presence of population 2. Right. So, we can do the exact same steps and procedure and arrive at an equation for population 2 as well. So, without repeating all the steps, let me write down the equation. So, the logistic term remains as it is. So, remember that this new term I am going to write now, that is the effect of competition. I will write that as alpha 2 1 n 1. Okay. To use the same colors on both the sides, let me write this also as alpha 1 2 n 2. Okay. So, the red term basically in both the equations capture the effect of competition on one another. Okay. So, now these are called Lotka-Volterra equations. So, now how do we make sense of these equations is what we will think about. Now, remember that the left hand side basically tells you the growth rate of population, and the right hand side tells you how it depends on the current population sizes of both species 1 and species 2. Okay. So, now how do we go about understanding these equation better? So, remember that So, how do we go about analyzing these two equations, which are basically called the Lotka-Volterra competition model? Let us call them equation number 3 and equation number 4. Okay. So, how do we go about doing this? Remember that we are going to focus on remember that when we studied the logistic population model, we studied the concepts of equilibrium and we studied the concept of stability. Recall that equilibrium basically meant a scenario where the growth rates are 0, which means if the populations are at those sizes or densities, they do not change any further. This is how we find the equilibrium values. What about stability? Stability basically means that if I now make a perturbation from the equilibrium, would the perturbation increase further or would the perturbations decay, and therefore I return back to the equilibrium. Okay. So, those depending on the perturbations, if the perturbations decayed, those are called stable equilibrium. On the other hand, if the perturbations increased, those would be called unstable equilibria. So, we are going to apply the same principles to understand what are the equilibrium and stability for the Lotka-Volterra equations. Okay. And we will also try to sort of argue intuitively and make sure that the mathematical results are meaningful along the process. Okay. So, now I need to be able to see these equations. Let us now look at how do we find the equilibrium. So, how do we find the equilibrium? To find the equilibrium, we need to set the growth rates to 0. In the logistic population model, there was only a single equation because there was a single population that we were studying. Now, there are here 2 species and therefore, we have 2 growth rate functions. So, at equilibrium, the new condition is that both the growth rates are 0. So, therefore, dn1 by dt is equal to 0. That gives us the condition that r1 n1 times k1 minus n1 minus alpha 1 2 n2 divided by k1, this is equal to 0. And now if I now set the equation 4 to 0, I will get, which basically means the growth rate of the species 2 population is also 0, I will get these. So, there are 2 equations which we have to simultaneously set them to 0. Okay. Now, let us identify various terms. Now, we have a product of 2 terms for so let me also label equations. Let me call this equation as 5, let me call this equation as 6. So, for equation 5 to be 0, that can happen in 2 different ways. Either this is 0 or the numerator here is 0. Okay. Likewise, for this equation 6 to be valid, I could have either this term to be 0 or the numerator here to be 0. Okay. So, under the conditions that both R1 and R2 are positive and they have a net positive growth rate at low population densities. So, R1 and R2 will be both greater than 0. So, so that means that the first part of the equation can be 0 if n1 can be 0. Okay. So, that I am now going to start enumerating all the 4 equilibrium. let me call the first, we will find 4 equilibrium as we will as we will soon see. I am going to enumerate all of them. The first equilibrium arises when the first term of the equation 5 and the first term of the equation 6 are both 0, meaning n1 is equal to 0 and n2 is equal to 0. Okay. Of course, if n1 is 0, if there is no individual of species 1, if there is no individual of species 2, there is no question of any reproduction or even competition, therefore, everyone stays at equilibrium, right. So, this is basically a case of extinction of both species. This corresponds to extinction of both species. Now, let us look at second equilibrium, which can happen when the first term here is 0, which is R1 N1 is 0, meaning N1 is 0, and the second term of the equation 6 is 0. Okay. And when N1 is 0, the second term of equation 0 basically means this numerator is 0. In this numerator, the last term alpha 2 1 N1 basically becomes 0. So, we basically effectively have K2 is equal to N2 or N2 star is equal to K2. So, and you would have noticed that I am using the notation star. Usually we use this notation star above the population variable to indicate that we are looking at equilibrium solutions. Okay. So, the second equilibrium solutions corresponds to species 1 is absent and species 2 is at carrying capacity. Only species 1 actually is present in this case. So, S1 is extinct, S2 is at carrying capacity, S2 survives at carrying capacity, right. Now, one can now easily guess the third equilibrium, which would be sort of inverse of the second equilibrium, where N1 is at its carrying capacity K1, whereas N2 will be extinct. So, S1 survives but S2 goes extinct. Okay. And we can obtain the third equilibrium by setting the second part of the equation 5, which is the numerator of the this term here, to 0, while setting the first part which is this to 0. Okay. Finally, we can also have an equilibrium where the second part of both the equations are 0. Okay. Now, this requires some effort to figure out. Okay. So, what exactly does it mean? The second part of both the equations 0 means that this would mean that K1 minus this term here, the K1 minus N1 alpha alpha 1 2 N2 is equal to 0. Okay. Simultaneously K2 minus N2 alpha 2 1 N1, which is the second part of the equation 6 is 0. So, let me rewrite those and rearrange. Okay. So, the fourth equilibrium can be obtained by setting the second part of both the equations 0, that basically corresponds to N1 plus alpha 1 2 N2 is equal to K1 and N2 plus alpha 2 1 N1 is equal to K2. Okay. Now, these are two simultaneous equations, those need to be solved, and of course, it is possible to solve for the values of these, and let me just write down and I encourage you to verify using the solutions for simultaneous equations, and these equilibrium turn out to be N1 star is equal to K1 minus alpha 1 2 K2 divided by 1 minus alpha 1 to alpha 2 1, whereas N2 star is equal to K2 minus alpha 2 1 K1 divided by 1 minus alpha 1 to alpha 2 1. Okay. So, these are the 4 equilibrium solutions. Now, I want to make a quick remark here. Okay. The equilibrium 1 2 3, they are always possible, they always happen, but the equilibrium 4 need not always exist depending on the values of alphas. Okay. Okay. Now, let us now, I know this has been a lot of mathematics now, we really would like to make sense of these equations in a biological setting. So, to make that a bit easy, let me simplify the notations. Let us denote alpha 1 2, which is is equal to alpha, which basically is the relative effect of inter-specific competition of S2 on S1 with the intra-specific competition within S1. I understand this is a really long complex sentence, but the basic idea is what we are trying to do is comparing. Now, let us say that we are interested in species 1, what we are trying to basically understand is species 1 has its own loop of intra-specific competition, right, and that we can sort of think of the effect of that as 1 unit. What alpha basically is the effect of species S2, the negative effect of species S2 on S1. Okay. So, now this is the way to think about this. Now, if alpha is equal to 1, this means that relatively interspecific and intraspecific competitions are equal. Are equal. On the other hand, let us say alpha is greater than 1, this means that interspecific is stronger. Maybe we could even think of a simple example. Let us say alpha is equal to 2, and let us go back to the Lotka-Volterra equation. Let us say if I have now replaced alpha 1 2 by alpha. So, if alpha is basically 2, it basically means that in this equation, in this part of the equation, for every one individual effect of one individual of its own species, and if I compare it with the effect of individual of species 2 has twice the effect as compared to its own type. So, therefore, alpha is equal to 2. Okay. And we can arrive at the same interpretations for beta, where basically beta is the effect of basically beta is the effect of species S1 on S2. Okay. And here too we have assumed that the relatively S2 influences itself the intraspecific competition with a unit of 1. Okay. Now, that is a very useful interpretation, and with that interpretation what we can do is as follows. We can draw this graph. What I will do is on the y axis I will represent beta, and on the x axis I will represent alpha. So, I want to clarify that I am not plotting beta as a function of alpha. These two are independent axes. Okay, think of them as take alpha and beta, x and y axis as two independent axes, and what I am now trying to do is divide this entire competition space into 4 quadrangles. So, okay. So, this intersection of the two lines at 1, value of alpha is equal to 1, value of beta is equal to 1, this if we have both alpha is equal to 1 and beta is equal to 1, it basically means that intra-specific competition and inter-specific competition is same for both the species. Okay. Remember that alpha captures the effect of the inter-specific competition effect of 2 on 1. Okay. So, this basically measures in some sense effect on species 1, whereas beta measures the effect of competition on species 2. The lower quadrangle where both alpha is less than 0 and beta alpha is less than 1 and beta is less than 1 means that for both the species intra-specific competition is dominant. Intra-specific competition is dominant, the presence of other species is of course influencing negatively, but not as much as its own type. So, if both the values of alpha and beta are less than 1. On the other hand, if both alpha and beta are greater than 1, I am in this space here, I am in this top right corner here. In this case, the interspecific competition is dominant for both species. Okay. Let us now come to the bottom right. So, in this case alpha is greater than 1, but beta is less than 1. Alpha is greater than 1, alpha greater than 1 means that species 2 has a stronger effect on species 1. That means that interspecific is dominant for only for S1. On the other hand, if I go to the left top here, interspecific competition is dominant only for S2. Okay, now we can try to make some educated guesses. Now that we have divided the entire parameter space of effects of competition of one another, we can sort of make some educated guesses about the possible outcomes, and we will see if those will be actually true. Let us make some educated guesses. Okay. So, in this space, in this space where let us look at this box here, where S1 has a strong negative influence because of S2. We could guess that here S2 wins, okay, whereas S1 goes to extinct. Okay. So, this means probably we might reach what I called equilibrium 2. In other words, this is same as equilibrium 2 will be reached, the system will reach equilibrium 2. On the other hand, imagine I am in this box here, which means that for S2 there is a strong interspecific competition, but S1 is not facing that. S1 has less amount of interspecific competition. So, here S1 wins is a possible outcome, which is sort of same as saying we are talking about the equilibrium 2, equilibrium 3. So, let us go back here. What was equilibrium 3 was N1 was k and N2 was 0, okay, that is correct. Now, what about these two? In the top right, where we have interspecific is strong for both of them are negatively influencing each other. Will both go extinct? That is a possible scenario. Okay. On the other hand, what happens in this case, where the interspecific competition is not dominant for either of them, it is actually intraspecific that is dominant. So, in this case that means that the other species is not negatively influencing a focal species as much as their own type, right. So, here we can guess that both will survive. And then therefore, we can have a coexistence solution. Okay. Now, coming back to think about this, let me go back to the top right corner again, where the interspecific competition is dominant. One possible scenarios will both go extinct. Again, think about that, is that a reasonable solution? What if when both of them are extinct, what if I now introduce a little bit of one of the two species, any one of them, but only one of them, then that can fully colonize the space and it will reach its own carrying capacity. What if I had introduced only the other type, right? Again, that would have been able to establish itself. Maybe there are alternative possibilities, maybe only one of them will survive, but which one will survive is not very evident, which is why we now need to analyze these mathematically and precisely, and it turns out that, let me tell you the answer to this, which we will analyze in the next video in a lot more detail. It turns out that our guess for both S1 wins, S2 wins are correct, as well as our guess for coexistence is also correct. It is the top right quadrant where interspecific competition is dominant, that is the most non-trivial scenario. That is where mathematical models tell us the following result, that it really depends on who is dominant in the beginning. If species 1 is numerically dominant in the beginning, that will actually outcompete the species 2 and it will establish itself, wiping out the other. On the other hand, if species 2 was numerically dominant in the beginning, that would outcompete other species and will eventually take over the entire space. Okay. So, we will analyze this more mathematically, but I hope that so far we have learned how to write down the effect of interspecific competition on top of intraspecific competition in a mathematical manner, which led us to Lotka-Volterra competition equations, and the terms there led to very nice interpretable meaning biologically, which can also be called competition coefficients alpha and beta, which I represented in the graph towards the end, and the relative values of alpha and beta determines the final outcome of who will win over the other. So, we will look at these final outcomes in the next video in more detail. Thank you very much.